Hey guys, it's Will Bartlett here, and I'm going to be presenting my Physics Lab 2 presentation. So what is this lab about? This lab is about Newton's second law, which is the momentum principle, as well as the effect of gravity and drag on an object.
And you'll see later in a model that the effect of gravity or the effect of drag on gravity is no comparison. And that's because the weight of this paper ball is so light that gravity is the strongest and most dominant force in this, and drag is effectively zero. However, drag still does have an effect on our object, and you'll see that in the graph.
So the observed data, as you can see, consists of a y value that is decreasing as time increases. Velocity here is not constant, meaning there is a drag force on this object. Now I'm going to show you guys the tracker video. So as you can see, the ball starts at the top and then goes all the way down to the bottom. This length is approximately 2.108 meters. So for the code for the model without drag, it required very little alteration. All it is that the net force is basically mass times gravity, and you also have to take in the unit vector of the position. The ball mass is 0.009 kilograms, and my ball was simply just two pieces of paper crumpled into one to give it a little more weight so we could see it. So these are the graphs that the model without drag produced. As you can see, the velocity versus time graph, it was linear, and a near linear velocity means that there wasn't a net force, so that makes sense.
So here's some important code to go over with the model with drag. On line 70, you have W is equal to the negative ball mass times gravity times the direction vector, J hat. On line 71, you have the force down is equal to the drag coefficient multiplied by the magnitude of the ball's velocity squared, all times the direction vector, J hat. And then on line 72, you have that the net force is equal to the W plus FD, so just the sum of those two values. So for the model with drag, on the far left, you have two arrows pointing up and down. The one pointing down is the gravity, the effect of gravity on the ball. As you can see, it is much bigger than the light blue arrow, which is drag force. And this makes sense as to why gravity is outweighing drag here, because as time goes by, you see this in the position versus time. As time goes by, the position is falling. So this means that the gravity is overdoing this drag force that we see. And then to back that up on the velocity versus time graph, you see that it's curved. And this does indicate that there was a drag force or another force present on this, because velocity is not constant during this time.
So here with some comparisons, on the far left, we have this big graph, and it's a comparison of everything. In the blue, you have the observed data. In the red, you have the model without drag, and then in the yellow, you have the model with drag. As you can see, the observed data and then the model without drag are very similar, and this is because the drag force on this ball was almost negligible. It doesn't really matter. Whereas the position with drag actually diverges at the end. So it almost seems as if it went less distance than the other two. And then on the far right, you have three graphs, and they're each respective graphs. And as you can tell, they look very similar, but when you look back at all of three of them combined onto one graph, they are different. So my thoughts. So drag did have an effect on the y position of the model with drag, but that does not mean that the observed position, this does not mean the observed model was affected noticeably though. The graph of the observed data versus the model without drag look more similar to the observed data versus the model with drag. This implies that Newton's second law applies because drag is effectively zero. So the momentum principle is perfect for this situation. And notice also how the second graph diverges way more at the end than the first graph. This indicates that drag did have some type of effect. But when you look at the graph on the left, you see that they're very similar. So you kind of have to moderate this. So being that they're so similar on the left, but then they're kind of different on the right, there is a drag force and it can affect and will affect this ball, but it's to the point where it's so small it's negligible for this situation. Thank you. Goodbye.